Hi everyone. So in this video, we're going to talk about some different terminology, some things that are used to describe acids and bases. So let's go ahead and get started. Okay, so the first term is amphoteric. So amphoteric refers to a species, so some kind of chemical that can either be an acid or a base. And whether it's an acid or a base depends upon its surroundings, so kind of how it interacts with its environment. So our first example of an amphoteric substance is water. So water can either act as an acid or a base depending upon what it is mixed with. So in our first example here, water, H2O, is mixed with ammonia. Now ammonia is always going to be a base, so the water is going to act like an acid. In this case, it is donating that proton, which if you think back to Bronsted-Lowry theory, bad bases accept, acids donate. Okay, so our next example, we have water mixing with hydrochloric acid. So in this one, the water is actually accepting that proton from the HCl, so that's why it's acting like a base. Now, water isn't the only substance that is amphoteric. Another common amphoteric substance is the bicarbonate ion, so HCO3 minus 1. When it's acting like an acid, it will give up its extra remaining proton to give us the carbonate ion, so we get CO3 minus 2. When it's reacting as a base, it's going to absorb that extra hydrogen ion to then give us H2CO3. Okay, so in this case, bicarbonate can act as either an acid or a base, meaning it is amphoteric. We also, as we saw with that H2CO3 with the bicarbonate ion, we have multiprotic acids, meaning we have acids that have more than one hydrogen on them. Now, monoprotic acids can only lose one hydrogen ion. So an example of this would be hydrochloric acid, HCl. Diprotic acids have two hydrogen ions that they have the potential of losing. So in this case, I have sulfuric acid, H2SO4, so it has two different hydrogen ions. I also have polyprotic acids, and these are kind of a generic term for anything that has more than one hydrogen ion it can lose. So we have phosphoric acid, H3PO4, which has three hydrogen ions that it can lose. Or we have sulfuric acid, which is also a polyprotic acid, having two hydrogen ions it could lose. Now, previously we talked about Arrhenius acids. We also talked about Bronsted-Lowry acid-base theory. Now we have Lewis acids and bases, and we're not going to focus on this a whole lot. If you go on to college chemistry, you will see this. Otherwise, what I want you to know for now, Lewis acids are ones that accept an electron pair. So if we look at the picture down below, the boron is going to take an extra pair of electrons, so that's shown in the product as having that extra line, so it has 8 electrons around it instead of 6 initially. And bases are electron pair donors, okay? So they're going to donate an electron pair to something else. So Lewis acids and bases, that's the final group we have for types of acids and bases. Now, as I said, we've already talked about Arrhenius, Bronsted-Lowry, and Lewis. So there's tons of different theories to think about and keep straight. So here are some mnemonic devices to help you out. So with Arrhenius theory, I want you to think, acid, because you're focusing on the hydrogens. Okay, that's the focus of Arrhenius theory. For Bronsted-Lowry theory, I want you to think bad. Bases accept, acids donate, like a sheep buying. Okay, I know it's a bad mnemonic, but it works. And then for Lewis theory, I want you to think Lewis electrons. So we're thinking about electron pairs with Lewis theory. Okay, so we already talked about water is really cool because it's amphoteric, but it can also do this thing where it self-ionizes with itself. Meaning, water can react with another water molecule to form hydroxide and hydronium ions. And this process is known as self-ionization. So if we look at the equation down below, I have two molecules of water. One of them is going to gain a proton, so H+, and one of them is going to lose that proton. So water can react with itself. And then finally, we have weak and strong acids and bases. Now, weak acids are ones that partially deionize. They partially break into the ions in solution, but you will still have some of those molecules stuck together, not breaking into their ions. Strong acids and bases will always completely break up into their ions as much as possible. Now, the term weak and strong can be used to describe both acids and bases. So if we have a weak acid, It's an acid that only breaks apart a little bit. Some of them have the ions, some of the molecules are still together. Weak base, same idea. Some of them will go ahead and ionize, some of them will not. Some will still be in their molecular form. Now, one thing I want to point out, and this is really, really important, strong acids and bases are not necessarily more dangerous than weak acids or bases. Strong and weak just talks about how many of those molecules break into their ions when they're in water versus how many stay together, not about whether it's safe. In particular, hydrofluoric acid, HF, is one of the most dangerous acids in the world, even though it's a weak acid. The reason why it is so dangerous, especially for humans, if it comes into contact with your skin, it's actually going to leach the calcium out of your body because fluorine's really greedy and it loves calcium. And that's really dangerous because we need calcium for our bone structure. We also need it for things like our heart to function properly. So even weak acids can be very dangerous, and sometimes strong acids really aren't that bad for us. So it's all a matter of what the actual compound is. Okay, so here is a list of the most common strong acids and bases. If it is bolded, I want you to go ahead and actually memorize it. And also remember if it's a strong or a weak substance. Okay, so hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. All of those are strong acids. For strong bases, I want you to remember that group 1 and the heavy elements in group 2 that form hydroxides are the strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and francium hydroxide. And then calcium, strontium, barium, and radium hydroxide. Okay, so those are the strong bases. And then for the weak acids and bases, okay, there's multiple different weak acids, but the ones I really want you to remember are acetic acid, what we have in vinegar, hydrofluoric acid, HF, and phosphoric acid. And then for the weak bases, remember ammonia. So I hope this helps. Please let me know if you have any questions. Otherwise, thanks for watching and have a great day, everyone. Bye.